So this question is about chemical bonds and energy involved in those. Which row is correct? So we've got to remember here is that bond, breaking a bond is a endothermic process, which means energy goes in. Making a bond is exothermic process, meaning energy is released. So we can't, anything that talks about the exothermic absorbing energy is immediately wrong, so we can get rid of those ones from our thinking. Endothermic reactions is energy being taken in, so that one isn't right. So the only option that we've got there, which is sensible option, is option C. We then got an example of a reaction taking place, and it wants us to calculate the energy change for this reaction. So what I like to do is just to draw these out. So I've got hydrogen, I've got fluorine, and then on this side I've got hydrogen fluoride, but there's two moles of it. Okay, so my first job is to work out bond breaking, what goes on in the bond breaking process. And I can see to break the bonds, I've got to break a hydrogen-hydrogen bond and a bond between two fluorine atoms. So I've got one lot of hydrogen-hydrogen. I then go to the table, I look that up, and that is 436, which is going to be 436. I've got a fluorine, so I've got one F and F, which is 1 times 158, which is going to be 158. I then add those together, and that gives me 594 as a total. On this side, let's do bond making. So what am I making here? Well, I am making two lots of HF bonds, which is 2 times 562, which is 1124. Okay, so I've got that as the energy from bond making. All I then need to do is do the 594, take away the 1124, and that gives me minus 530 kilojoules per mole of energy. Okay, and then the last question, I think it's the last question, yeah, a 6-mark question here. This is quite a good question. So we've got an energy profile for an uncatalyzed exothermic reaction. And it then says, use examples of catalysts, discuss what catalysts do, their effect on activation energy, and you can illustrate figure 8 to do your answer. So let's illustrate it as well. What I have done in my illustration, I have drawn the reactants on, show where the reactants are, and up to here, this is the activation energy. And then I've drawn on this dotted line here is the activation energy when we have a catalyzed reaction. And if I don't want to make this too messy initially, but if I do that coming back to here, then you can see that that activation energy is far smaller. So you need less activation energy in order to make that reaction work. Okay. So key points in our answer. So we've illustrated, which is great. We can reference that in here. So I've said that catalysts speed up chemical reactions. They do this by lowering the activation energy. They provide an alternative pathway for the reaction, and they are not used up in the process. This means low activation energy, so I'll probably link that into here. This means that there are more particles whose energy is greater than activation energy, and therefore there's more particles that can react. So it's quite a lot to that. I've boiled it down to a few bullet points. The second part of this answer, though, is then talking about some examples. So we know that we have studied the Haber process this year, and that uses an ion catalyst. So an ion catalyst to make the ammonia. So we can give an example of that one. You've probably seen the cracking demonstration. So cracking uses a catalyst. in its reaction. I'm trying to think of other examples we have done in class. We've talked about catalytic converters, which are used in car exhaust to reduce the harmful emissions being produced. And I think that would be plenty to explain in your answer.